okay, the transfer function g of j omega equals to 5 plus j omega, the corresponding Nyquist plot for positive frequency has the form. Okay, we need to find the Nyquist plot directly. Okay, how the representation would be. Simple question, no need to follow any of the rules. We will see directly by a substitution method. Okay, what is the formula given? G of j omega equals to 5 plus j omega, right? Till this point it is we know. Let us assume omega equals to 0 here. Okay, omega equals to 0 here. Okay, then g of 0 would be 5. Yes or no? Omega equals to 0, g of 0 will be 5. Omega equals to infinity, g of infinity would be infinity only. Let us see from the options. When this is my omega plot, so when omega is 0, my value is 5. Yes, my value is 5. When my omega is infinity, somewhere there, it is going to infinity. So this would be one of the possible option. There is nothing to do with these both options, because this is a simple equation with no poles. Okay, only zeros are existing in this. Okay, so either we are going to get a straight line only, that's it, nothing more than that. This one option, students may get confused. This is the point where not omega equals to 5, omega equals to 5j, this point, not omega equals to 5, it is the point where omega equals to 5j, not omega equals to 5. So this is absolutely the wrong option. Only option A is the direct option and correct option. Okay, so this is the simplified process you can learn in this way. Some of the options where only zeros are given, some of the questions where zeros are only given, you can directly substitute 0 or infinity, because in time response or in frequency response, anywhere only 0 and infinity are both points where we are going to see how the system is getting started and how the system is getting ended. Okay, so at this particular point we have done 0 and infinity analysis only particularly, and we have found the right option. Okay, simplified versions we can try in exams also. Next, so a stable system with transfer function g of s is given. Okay, some complex equation is given where b1, b2, b3 and till bp, b1, b2, b3, bp, okay, and a1, a2, a3, aq, a1, a2, a3, aq sum till are real value constant. There are some constants. The slope of the Bode log magnitude curve is, what is the slope? Minus 60 dB per decade. Simple again. What is the slope? Slope given as minus 60 dB per decade, which is nothing but, okay, poles are dominant. How many dominant? 3 poles are dominant, which is nothing but 3 into minus 20, we are going to get minus 60, exactly, right? So in the top, let us consider p for top numerator for zeros. My constant, what is the constant? They considered p, and for poles they have considered it as q. Okay, small p and small q. Okay, like what is the p and q order? Highest order. Suppose my p is 4, q is 3. So p is the order of zeros, q is the order of poles. Okay, so to get the dominant as 3, when we are going to get it as 3, then we are going to get exactly the value would be value of slope would be minus 60. So my p minus z, okay, p minus z should be is equals to, sorry, not p minus z, poles minus 0 should be is equals to 3, exactly 3. Why? Because it is going to have minus 60 dB per decade. What is the value of poles here? Poles are represented by q, small q, and zeros are represented by z, small p. Q minus p should be equals to 3. This is the main equation which we have considered. After this point, we need to see the options. So where q minus p will be 3. Firstly, in option A, q will be 3, p is 0, so q minus p is 3. Here we are going to get 3. Again here, q minus p should be 3. 7 minus 1, 6. So this is the wrong option. Next, q minus p, 3 minus 2. Okay, 3 minus 2 is 1. So this is also the wrong option. Q minus p, 5 minus 3, 2. Again, this is also the wrong option. The right answer is 3. So option A is only the right answer. So here the value of p is 0 and value of q is 3. So by this we can say, as per this equation and as per the solution which we have got for this particular question, q is 3 nothing but the order of denominator would be something 3 cube, and in the numerator we will not consider, we will not have any zeros, like there will be some constant k or some constant 1 or something. Okay, so option A is the right answer. Next question. So the Nyquist stability criteria and the Routh criteria are both powerful analysis tools for determining the stability of feedback controllers. Yes, that is the right thing, but we need to identify which of the following statements is false. Okay, let's see the options. Both criteria provide information related to the stable gain range of the system. Yes, in the root locus or in the Nyquist stability criteria, we will find the stability analysis, stability range or everything. So this is the right answer only. The generated shape of Nyquist plot is readily obtained from Bode magnitude plot for all minimum phase system. Yes, from the Bode magnitude plot, we can find the Nyquist plot for only all minimum phase systems only. When the system is stable, then we can find the Nyquist plot from Bode plot also. This is also the right answer. The Routh criteria is not applicable in the condition of transport lag, which can be readily handled by Nyquist criteria. Exactly. This is only the limitation of Routh criteria, which will be handled by Nyquist criteria. This is also the right option only. The closed loop frequency response for a unity feedback system cannot be obtained from the Nyquist plot. Why? We can easily obtain a closed loop frequency response, which is nothing but we can determine the transfer function. We can analyze the transfer function through Nyquist plot also. So this is the wrong option. But here he asked the false statement, which is a false statement. So as per the false statement, this is only the right answer. Okay, this is the false statement in the given all statements. Understood? Next question. So the polar plot of an open loop stable system is shown below. Okay, so the closed loop system is stable, marginally stable, or what is the case we need to see. Okay, let us see this. So let us draw the mirror of the way how the path of the polar plot is going to travel. Here firstly it will travel in this direction also. So in this way it is going to travel like this, and next there is also one more way. So here it is going to travel in this way, so to the upward direction. Again at this some particular point it will again travel in the same way to the same point again till omega equals to 0 and till omega equals infinity, they both are going to travel. So the number of encirclements for at -1 comes somewhere here, -1 is going to exist. So -1, 0 would be 2. So 2 in clockwise directions only, both are in clockwise, not in anti-clockwise. So we have n is equals to 2 here, but as it is clockwise, so we are going to get minus. If it would be anti-clockwise, the sign would be +2 only. And next, what is the value we have? N is equals to equation n is equals to p minus z. Okay, if let us consider for this particular case, for one case, let the system would be stable. If the system is stable, then the poles should be 0. Okay, the number of poles should be 0. So what is the value of 2? N is equals to -2 is equals to number of poles are 0 minus z. Okay, 0 or z. So minus cancel, z is equals to 2. Here there are 2 zeros. Now if there are 2 zeros existing, then suddenly my system would be in marginally stable and unstable state. But unstable with one pole on the RHS, unstable with 2 poles on the RHS side. If we are considering 2 zeros, then we need to have 2 poles also. Then only the Nyquist encirclement would be equals to 0 here, exactly. So the system would be unstable only with 2 poles on the RHS plane. Now currently, like in this case is wrong actually, but if it would be unstable, then 2 poles should also exist. But here there are 2 zeros, so the system is marginally stable only. Actually it should be unstable, but if we are going to find exactly the encirclements with the process, then we are going to get unstable case. But here as per the options, the answer would be marginally stable only. Okay, next question. So the transfer function y of s by u of s of a system is described by the state equations. So a state equation is, 2 state equations are given. We need to find the transfer function. Okay, so the equations given are x asterisk of t equals to -2 x of t plus 2 u of t. Let us directly take the Laplace transform of this. Laplace transform, apply Laplace transform. Okay, s into x of s. This is the differentiation model. So s into x of s is equals to -2 x of s plus 2 u of s. Okay, this is the first equation. Okay, the second equation is y of t equals to 0.5 x of t. We need y of s by u of s. So firstly we'll take this into x of s form. So sending this side, s into x of s plus 2x of s is equals to 2 u of s. Okay, so x of s is equals to 2 u of s by, this goes here, and s plus 2. Okay, at this particular point it is 2 u of s by s plus 2. Next, this is let this be one equation, one transfer function equation. Next equation is y of t equals to 0.5 xt. This simple equation. When we apply Laplace transform to this, y of t equals to 0.5 x of t. So when we applying Laplace transform here, so we will get y of s is equals to 0.5 x of s. So this is the equation 2. Let us put 1 in equation 2. Put the equation 1 into 2. Then what are we going to get? Y of s is equals to 0.5 into, what is the equation? 2 u of s by s plus 2. So it would be 2 u of s by s plus 2. We need the value of y of s by u of s. So after solving this, we can get the equation as y of s is equals to 0.5, like sending this into this side, u of s, totally this would be equals to 0.5 into 2 would be just 1 divided by s plus 2. So this is the final equation which we have got. So from the options, so 1 plus s by 2, option D is the right answer. So resolving this state equation, we have got the exactly transfer function which they asked y by u, y of s by u of s. Okay, next question. So zero input response of the system is given by, there are some equations given, some state equations are given in the matrix form. So we need to find the zero input response. So let us firstly resolve those, what are those equations are. So x, differentiation of x dot of 2, x dot of 1 and x dot of 2 are given as 1 0 1 1 into x1 of t and x2 of t. So we have, from that, matrix A is given as 1 0 1 and 1, and zero input response, which is x1 of 0, first initial input response, x1 of 0 and x2 of 0, this would be 1 and 0. Okay, 1 and 0 exactly. So what we have, formula is Si minus A whole inverse into zero input response, initial input response, x of 0 into x of 0. Okay, this determinant we need to find exactly to find the zero input response. So the formula is 0 to find the actual state input. Okay, we need to, the zero input response is given. Okay, we need to find the actual, what is the input of the system, input, actual input. So let us find the Si minus A firstly. Si minus A is equals to S0 0S Si, this is Si, and next A, what is my A? 1 0 1 1. So from this I'll get S minus 1 0 minus 1 S minus 1. Okay, this is the Si minus A. Now let us find Si minus A whole inverse. Si minus A whole inverse would be inverse of this. So what would be the inverse of this? A, B, C, D. Then we are going to get dA, BC and minus minus of B and C. So here we will get S minus 1 0 and 1 is multiplied with minus here. So minus 1 is multiplied with minus, so 1, and again S minus 1. Okay, this is the point. S minus 1 0 1 and S minus 1 again. Okay, so and divided by det. So what is the det of this equation? S minus 1 into S minus AD minus BC. So S minus 1 into S minus 1 whole square. So S minus 1 whole square. Okay, S minus 1 whole square minus BC. B into C is 0, so obviously we are going to get this thing. Okay, now let us multiply them inside, the denominator into inside. This is minus 0 only, so just put it like this. Si minus A whole inverse would be equals to, multiplying there we will get 1 by S minus 1, and the second term is 0, and 1 by S minus 1 whole square, again 1 by S minus 1. Okay, this is the value of Si minus A whole inverse. Now we will multiply this with our equation and take the Laplace transform, inverse Laplace transform of that. So the thing is, input response we are getting like this, but we are going to take the Laplace inverse of whatever we are going to get of this and multiply with the x of 0 output response. So now we will take Si minus A Laplace inverse. So L inverse of Si minus A, this is also again inverse only, Laplace inverse. Okay, so we are going to get Laplace inverse of 1 by S minus 1 would be T. Okay, next Laplace inverse of 0 would be 0. This is e power t, not t, e power minus t. Next 1 by S plus 1 whole square would be, sorry, it is minus, so we are going to get e power plus only. Okay, next 1 by S minus 2 S minus 1 whole square would be t e power t. Okay, since it is multiplied square, t is multiplied. If it is cube, then t square is multiplied. Next, the last one is again minus 1 by S minus 1. So again we are going to get e power t. So now this should be multiplied with initial response. So L inverse of Si minus A whole inverse into x of 0. Then this would be e power t 0 t e power t into, what is my actual input? 1 and 0, initial input. So 1 and 0. Multiplying these both, we are going to get, first point is e power t and second one is t e power t. That's it. Because however these both values of 0, e power t into plus 0 into 0, and this into this plus 0 into 0 this. So finally my input of the system is e power t and t e power t. So as per the options, my option C is the right answer here. Okay, simple mathematics only, matrices. What we have learned: inverse, det, and Si minus A. Finding the one formula, Si minus A, and finding the Laplace transform. Three combination of these three concepts, we are going to get the state space formulas. Okay, simply we can solve this equation. Solve these questions. Next question. So for the system described by the state equation, some state equation is given. Okay. A, B, both we can consider it as. If the control signal U is given by this, we need the eigenvalues of the system. Just we need to find one matrix. From that we need to take the eigenvalues. What I'll do, U is related here something. So directly first I'll substitute, because X is only the term here. No Y or no other term is included. So I'll put this U here and find the actual matrix. For that matrix directly we'll find the eigenvalues. Okay. So from the given one, X dot is equals to 0 1 0 0 0 1 0.5 1 2 into X plus 0 0 1 into U. What is my U? This. I'll substitute directly here. So my X dot would be 0 1 0 0 0 1 0.512 into X plus 0 0 1, okay, 0 0 1 into minus 0.5 minus 3 minus 5 into X. Similar, both are the same. So we multiply this, we'll get some 3 by 3 equation. We add those both, we'll get one set of matrix. That matrix will find the eigenvalues. That's it. So let us assume this as equation A. We'll write again in the next one. Plus 0 into something is 0, 0, 0. Multiplied. Again multiply, we will get second row also 0. Third row is multiplied, so we get minus 0.5. It is multiplied with 1, so minus 0.5, minus 3 and minus 5 into x. This has the same variable, this has the same variable. We can add these both matrices. Then we are going to get 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0, 0, again 1. So 0, 0, 1, minus 0.5 plus 0.5, 0, 1, minus 3, minus 2, minus 5, 2, minus 3 into x. So x dot is equals to my whole this matrix A into x. So I have got a finally one matrix. So what is that matrix? 0 1 0 0 0 1 0 1 0 0 0 1 0 1 0 0 0 1 0 minus 2 minus 3 0 1 0 0 0 1 0 minus 2 minus 3 is my A state matrix, which we have got from by solving that. Now directly we will find the eigenvalues for this. What is the formula for finding eigenvalues? Si minus A whole inverse should be equated to 0. Okay, so what is my Si minus A? Firstly, Si minus A would be S0 0 0 S0 0 0 S Si minus A 0 1 0 0 0 1 0 minus 2 minus 3. Okay, next solving this we will get Si minus A S minus 1 0 0 S minus 0 is S, 0 minus 1 is minus 1 0 0 minus of minus 2 is plus 2 Si minus 3 S plus 3. Okay, this is the only variable which we are getting S plus 3. Okay, this is Si minus A. Okay, preliminarily this is the thing. Next, Si minus A whole inverse we need to find. So we need to take det and adjacent of the whole variable also. Sorry. As we are finding Si, Si minus A over inverse should be equals to 0. No, not Si minus A whole inverse. Sorry, there's a small mistake. Si det of Si minus A should be only equals to 0. There is no need of Si minus A whole inverse. So let us take the determinant for this, and this should be equals to 0. Then we can find the eigenvalues. So directly Si, like we have these both as 0. So when we are taking det, only this variable is taken under consideration, and both are multiplied. S into S plus 3 minus 2 into minus 1 is minus 2. So here I will get minus 2. Okay, this should be equated to 0, because however these both are 0, only this variable can be multiplied in the det. Okay, so here I will get S of S square plus 3S plus 2 is equals to 0. Okay, this S can be sent here, it can be cancelled easily, and S square plus, sorry, you cannot cancel, sorry. S is equals to 0 will be one of my eigenvalue, and next S square plus 3S plus 2 is equals to 0. So S square plus 2S plus S plus 2 is equals to 0. This is, from this we will determine two more. So S of S plus 2 plus 1 of S plus 2 is equals to 0. So S plus 2 into S plus 1 is equals to 0. S is equals to minus 2 comma minus 1. These are my other both eigenvalues, and this is one of my eigenvalues. So totally S is equals to 0, minus 1, minus 2 are my eigenvalues for that particular given thing. So 0, minus 1 and minus 2. Option A is the right answer here. Understood, students? Let us move on to the next question. Simple. We need to apply matrices only. Next question is given as some equation is given. Consider the dx by ax. Dx by dt is nothing but x dot of is equals to ax plus bu. Okay, it is given in this form. A is given, b is given. Okay, arbitrary. Which of the following statements are true about controllability? What is the formula of controllability? Just keep it in mind. Direct one formula. Controllability C is equals to, you can controllability of a system, so C of X or C of B, something, many notations would be given, would be taken as B, A B, A square B, so on until A power n minus 1 into B. What is this representation? Let us suppose B is 1, B we have PQ, AB will get some other value, let us assume 1 comma 0. So this will be another matrix. Again we'll get some A square B also. If the system is more and more, like we have two matrices only here, A and B only, we will only proceed till this point only. This is not required. When n number of matrices are going to increase, this is for 3, this is for 4, 5, 6, 7, and this is for n number of matrices, we will apply all this. So this whole is considered, let us consider A square B is 1 comma 0, again A cube B is 1 0 comma 1, so on. We will write those equations into a single matrix, and then we will determine the stability or controllability of the system by taking the determinant. But here this whole is not required. We are only having B, A, B, because there are only two matrices. So here controllability of the system can be taken as Cx, can be taken as B and AB only. B value we can directly put PQ, but let us find the value of AB. So what is that value? If the system is controllable, okay, the condition is equals to 0, uncontrollable. Okay, not equals to 0, not equals to 0, it is controllable. Understood? So Cx, okay, we'll find AB, det of Cx should be not equals to 0 or equals to 0. Okay, so let us find A into B. A into B is equals to, what is A? 1 0 0 1 into P Q. Okay, so multiplying these both, we'll get the first one P into 0, P plus 0 is P, and 0 into P, this is Q. So I am getting A into B as PQ. So taking it as C of X det, we will get first, what is B? What is B? PQ. What is AB? AB is also PQ. Taking the determinant of this, we will get multiplied these both diagonal and that both diagonal and that their difference. So PQ minus PQ, which is 0. If I am getting my determinant as 0 for a controllable problem, then what is the case? The system is, sorry, I have done a small mistake here. The case is just reverse. Then the system is going to get 0, like if it is not equal to 0, if it is equal to 0, then the system will be uncontrollable. Right. Okay, no mistake. If the determinant is equals to 0, the system is uncontrollable. If the determinant is not equal to 0, then it is controllable. Now my determinant is equals to 0, then the system is uncontrollable for all values of P and Q. However you do for any value of P and Q, the system is going to be only uncontrollable only, no change. Okay, next question. So system X differential X dot is equals to Ax plus Bu, normal state equation. A and B are given. We need to find the stability and controllability. First we'll do with the controllable thing. Okay, what is the value? Cx is equals to B, AB, A square B, those all are there, but what do we require? Only B and AB. Why? There are only two matrices given here. So let firstly B is also there, 0 comma 1. Let us find AB. This det should be equal to 0 or not equal to 0, whatever it would be, we will find that. Okay, so AB would be, the value of AB would be, what is A? Minus 1 2 0 2 into B would be 0 1. Multiplying this, we will get minus 1 into 0 0 plus 2 into 1 is 2. Okay, 0 into 0 is 0, 2 1s are 2. So AB value is 2 comma 2, and putting it in the controllability mod, we will get mod of, what is the value of B? 0 and 1. What is the value of AB? 2 comma 2. Sorry, this is determinant, so we are putting like this. So taking the det, 0 into 2 is 0 and 1 into 2 is minus 2. We are going to get minus 2, which is not equal to 0. So the system is controllable. Okay, the system is controllable. So whichever the options are uncontrollable, we can directly eliminate those. B and D. See, they are uncontrollable. The system is controllable here. But it is stable or unstable. We will decide that. Okay. So what is the value? What is the equation to find transfer function for these type of state models? B into Si minus A whole inverse into C. However, C is not given. So we will eliminate that. Si minus A whole inverse na. First let us find Si minus A. Okay. What is the value of Si minus A? A would be minus 1, 2, 0, 2. Okay. S0, 0S into minus A. What is the value of A? Minus 1, 2, 0, 2. Minus 1, 2, 0, 2. Okay. So minus 1. Okay. S minus of minus 1 is S plus 1. 0 minus 2 is minus 2. 0 minus 0 is 0. S minus 2 is S minus 2. Okay. These all are put here. Si minus A. Now let us find Si minus A whole inverse, which is nothing but A, B, C, D. These both are exchanged their places. So we will get DABC, which is nothing but S minus 2, S plus 1. And these are multiplied by minus. So we will get 0 and 2 here. Whole divided by the determinant. What is the determinant here? AD minus BC. What is the determinant here? AD. What is the multiplication? S plus 1 into S minus 2 minus BC. BC is nothing but 0. See, here we will do a small observation. Si minus A whole inverse, this whole we should put here to get the transfer function. Okay, fine. If C will be given, then we will see with C. B is also given. Then B will be multiplied with this equation and it will be in the numerator only. Okay. If C is also given, it will be multiplied with this matrix and it will be in the numerator only. But what is the denominator here constantly? This is my denominator, which is nothing but when in a transfer function, the denominator indicates the number of poles or what is the value of poles. So what we will do to determine the stability of the system, we will check with the poles. So here let us see with the poles. S plus 1 into S minus 2 is equals to 0. This is my equation of denominator and poles. So what is the value of S? Minus 1 comma 2. Minus 1 comma 2. Minus 1 left half of S plane, but 2 right half of S plane. So my system is not going to be stable also. So unstable system. So we can say my system is controllable but unstable. Stable is not the right answer. Okay. So in this process, we have found the stability, controllability in two steps only by this formula, and stability by this similar formula, but a small logic is applied here. Okay, simpler way. We need to find the simpler way and time consuming should be decreased here. Time should be consumed. Okay. So in this process, we need to find the value of stability, if it is controllable or stable. We need to determine what is the value of after controllability. What is the value? Then if the examiner asking that way, then minus 2 is the answer. Okay. Next question. The state transition matrix of a system is given. Okay. So some state transition is given. Okay. No. Some matrix is given. We need to find the state transition matrix. Okay. To find the state transition matrix, what is the value of A? 0, 1, 0, 0. Okay. What is the value of state transition matrix pi of t? Simpler one, Laplace inverse of Si minus A whole inverse. Direct formula. Nothing much complex in this. Okay. So let us find Si minus A first. Si minus A. S0, 0, S. Si minus what is my A? 0, 1, 0, 0. From this, I will get S minus 0 is S, 0 minus 1 is minus 1, 0 minus 0 is 0, S minus 0 is S. So I got my Si minus A. Now Si minus whole inverse. Si minus A whole inverse. So inverse of Si minus A is nothing but A, B, C, D would be, these both will exchange their positions. So it doesn't matter. S. B and C will be multiplied by minus, so 1 and 0. Okay, now the determinant of this S into S is S square AD minus BC. 0 minus S is 0. So what are we going to get here? S by S square will be, okay, let us write this, S by S square, 1 by S square, 0 by S square, S by S square. From this I am going to get S by S square will be 1 by S, 1 by S square will be 1 by S square, okay, 0 by S square will be 0, S by S square will be 1 by S. Okay, this is the process. Next we will multiply we will do the Laplace transform for this whole equation. So inverse Laplace transform of Si minus a whole inverse would be Laplace inverse of 1 by S, 1 by S square, 0 and 1 by S. So what is the Laplace inverse of 1 by S? 1 by S square is t, 0 and 1 by S is again 1. So 0 will get 0 only. 1 by S Laplace transform is u of t, which would be 1 in the time domain to normal complex conversion, and 1 by S square is t u of t, but we can take it as t, and 0 and again 1 by S is 1. So from the options the right option is D. Option D is my right option. 1t 0 1. 3 steps only. First Si minus a whole inverse, Laplace transform for that, complete. Or whatever the state transition matrix asks for any of the system, we can find in this way. Okay, next question.